Everyone, this is a video to go over lesson 6.5 on the average value of a function. So this is our last lesson where we talk about an application of integrals. So we're going to be calculating, so given a curve, so let's say looking at this curve f of x drawn here, what is the average y value of this function? We could guess it might be somewhere in the middle. But we're going to be learning a formula to calculate the exact, maybe it's there, I'm not sure, the exact average value of the y value along the curve. Let me just show you a little animation here to maybe make it more clear of where this formula is going to come from. So here's another curve. Maybe our prediction, maybe the average value might be somewhere here, for example. So really what we're trying to do is like the area sort of in white here that's below this orange line, we want to make that equal to the area that's above the orange line. And that way it's going to sort of balance out. We can see that in the next one here. This is the actual average value of that curve in the dotted black line. And you can see the red area above the dotted black line matches the red area that's filling up below the black line. So let me draw that in a picture and we're going to develop the formula from that. Okay, so here's our curve. I'm just going to erase what I already had. Okay, so let's say the average value is exactly here, okay? Then this area here is going to equal exactly this area here. Another way to think about this is the area under the curve, the integral of f of x dx from a to b. I'm going to draw that in blue. That's going to be exactly equal to if you made a rectangle with this average value right here with a height of the average value, we'll call that f av for short, and the width is this width of the interval that you're looking at, so it'll be b minus a. That's going to be identical to the area under the curve because these two pieces are going to match exactly these pieces that are above and below. So the area of a rectangle is length times width would be b minus a times f av. And if you just move the b minus a to the other side, we have our formula for the average value. So that's how they developed this formula. I don't need you to be able to derive it, but here is the formula. Okay, so the b minus a is moved to the other side, so it's 1 over b minus a times the area under the curve from a to b. So that's the average value formula. We're going to now try it out on a function. Another way to that I remember it is like if you think of an average value of like a bunch of numbers, right? We add them all up and then divide by how many numbers there are. It's kind of similar here. This is the adding them all up part. So you're adding up all of the values of f of x kind of, and then you're dividing by how many values you have or the width of the space you have. So it's kind of similar to the finding an average of a bunch of numbers. Okay, so here's our function f of x. So the formula for f average is 1 over b minus a to b f of x dx. So for us, our interval is from -1 to 2. So it'd be 2 minus -1. And I'm going from -1 to 2, 1 plus x squared dx. Let's start a new line. So 2 minus -1 is 3. So the width of the interval is 3. And I'm going to do the antiderivative here. So we have x plus 1/3 x cubed evaluated at 2 and -1. And if you plug that in, you get 6. So it's 1/3 times 6, which is 2. So the average value of f of x on -2, which is -1, 2 is 2. Okay, so that's it. It's just applying a formula, so it's pretty straightforward. There's one theorem that goes along with this idea, though. And I like to think about this with an analogy with cars. So let's say you're driving to school and you calculate that your average speed, you calculate the time it takes you to get there and the distance it is, and you figure out that your average speed was 40 kilometers an hour. Okay, so your average speed was 40, then, but you're not going 40 kilometers an hour at every single point on your journey to school, right? You're sometimes going a little bit below 40, sometimes a little bit above, but the average speed you're going is 40. This theorem says that you must have been going 40 at least one moment in time, on one moment on your journey. You can't be sometimes below 40 and sometimes above 40 and never actually 40. If you have a continuous function, then you're always going to hit the average at some point in the interval. That's what this theorem basically says. So let's read it. So it says if f is continuous, so if you're drawing, so most functions we're going to be dealing with are continuous, right? You draw them without lifting your pen. Then there exists a number c, so one point in your interval, at least one, where f of c is the average. So you must hit the average at some point in your interval if the function is continuous. So let's just look at this example here. So here's the average shown. This would be the c they're talking about, and this would be f of c, which is the average point. Okay, so you must hit the average at some point. So let's do this with the same function we were just working with, 1 plus x squared. We already know the average value is 2, so let's see if there's a point on this curve where this function is exactly 2 between -1 and x equals -1 and x equals 2. Let's apply this theorem. Okay, and we know this is continuous, right, because it's a polynomial. So let's find this number c. So we want to make sure that f of x equals 1 plus x squared. So we want to find a place where, or I'll use the number c actually instead of x. So we're looking for this magic number c where the function is exactly equal to the average. Remember, we already calculated the average from example 1. Okay, so let's just solve this. Yeah, that's right. Let me just check my notes. Yeah, oh yeah, okay. So then we're going to subtract 1 from both sides. We'll get c squared equals 1. And we take the square root of both sides. We get c equals plus or minus 1. So there's actually, in this case, 2 points on the interval where the average is exactly, or where the function value is exactly the same as the average. So therefore, there are 2 points in -1, 2, where f of x equals 2. And then I'll list them here. We have one at -1, 2, and another at 1, 2. Let's see what that looks like in Desmos if I graph it, and we can have a look. Okay, so this is a good way to check your work if you're doing your homework, to visualize if you've got it right or not. So let's bring up Desmos. I'm going to be graphing my function 1 plus x squared only on the interval -1, -1 and 2. Let's just turn off the grid and put it on projector mode so I can see it better. Okay, so here's my function. Remember the average was exactly 2, right? So here's the average. And look, there are the 2 places where my function is exactly to the average. So let's show a little picture of that. I will put it in the notes. There we go. Okay, so we found our 2 spots at x equals -1 and x equals 1. The function value has the exact same value as the average value. And this theorem, the mean value theorem, states that those points must exist. Okay, and that's it for today's lesson. It's a really short one. So I'll just stop the recording.